Right, sorry for stalling. So, Cantor set. We mentioned in last class that what is the Cantor set? It's if you take R and you begin constructing it from the interval from 0 to 1, and you construct it by removing open middle thirds. So it means that the first level is going to be the first third and the last third. And then each of those is, from each of those you remove middle thirds and something survives. And as you can see that I can say that when I look at the Cantor set, it's really the same thing as simply taking the intersections of n starting from 0 to infinity of I sub n. And there are plenty of points that survive because when I look through those intersections, I can select a point by going through a particular sequence of decreasing nested closed intervals. And as you can see that the length of the interval is, on the nth level, is 1/3 to the power of n. So the length of the interval decreases to 0. So each particular path of left and right identifies a particular point in the Cantor set. And therefore, as we said in the last class, I can say that the cardinality of the Cantor set is in fact the same as the cardinality of all infinite sequences formed out of left and right. Okay, so if I select any particular sequence of left and right, that corresponds to a unique address for a point in the Cantor set. And as we mentioned in the last class, this set is the same as the set of all attendance rosters for the natural numbers n, right? So I can think of L as absent and right as present, so I can then, instead of saying sequences of left and right, it's the same as sequences of zeros and ones, right? So that's the same as the set of attendance rosters for n, which, if you remember, if you did the homework, that corresponds to 2 to the power of aleph naught, which is the same infinity as the infinity of the real numbers. So this set is, its cardinality is as large as that for the real numbers. So we want, so we're going to say it's uncountable in yet another way. So let's try to figure out if there is a natural representation for sets in the Cantor set. So the question here, what is the natural representation for elements of Cantor set? What is a natural representation for points in delta? So do you remember what real numbers are supposed to do? The real numbers are concerned with measurements. If I ignore for a moment the question of convergence, real numbers are all the geometric points that can be expressed as an infinite sum of fractions. Okay? So a real number is any number that can be expressed as an infinite sum of fractions. The rational numbers are those that can be expressed as a finite sum of fractions. So every finite sum of fractions you can easily extend it to an infinite sum. So what might be a good representation? In base 10 system, in a decimal system, what do? You count in powers of 10. So you have 1 through 10, and then you have 10 squared, 10 cubed, 10 to the 4th power. So powers of 10, and then if you go in the other extreme, you can take the number line, the interval from 0, 1, cut it into 10 parts. And then see which part you pick, and then cut the other into 10 parts. But here, notice that there's something else that is more natural. You see, I partition the interval into how many parts? Into 3 parts. Okay, so what we can do is, let's try to represent it in terms of powers of p. let's consider powers of 3. So what is that? Powers of 3. So if I look here, the points in I1. So if I look at the points in I1, I can represent this number as 0.0. So this is 0.0. And that's of course in base 3. Okay. So what I have here is I don't quite move that far to 3. The middle guy here is 0.1, and the last guy is 0.2, and that is in base 3. Well, if you don't understand in a moment, I will write it. Right. So what is this guy? This guy is 0.00. This guy is 0.02. The middle guy is 0.01. This guy is 0.20. The middle guy is, of course, 0.1. This guy here is 0.22, and the middle guy is 0.21. Because think about it. What is it that we do when we do measurements? Why is it an infinite sum of fractions? Let's say what you do is you advance by a certain fraction. So in this case, how do I find points in this interval? I cut it into 3. If I advance by a full 1/3, I am out. If I advance by a full 1/3, maybe the exception is the point 1/3. It's exactly from 0 I move by a segment of length 1/3. But every point that is bigger than 1/3 here, in fact, I need to advance by more than 1/3. Right? I first have to advance by 1/3, and then I add a fraction that is smaller than 1/3, so that I don't skip to the next interval. Do you see that? So for example, so what I mean is what we have is in I1, we move. Let's say here is that number line again. So if I want to represent a point in here, I have to write 0 divided by 3 plus something over 3 squared. And that something is at most 2. Okay? That would be representing points in here. Do you follow me? So in general, we already did this as a special statement before. So if you have x belonging to the interval 0, 1, then x can be expressed as an infinite sum. And the infinite sum will be n equal 1 to infinity of something of the form b sub n divided by 3 to the power of n, where bn is either equal to 0 or to 1 or to 2. So, in other words, we will say that x is equal to 0.b1, b2, etc., and we call it base 3. Remember, we did it somewhere early in the semester. We spoke about base p. So we don't necessarily prefer base 10. Sometimes we prefer other bases. In the Cantor set, the natural basis is in terms of 3. Because you cut the interval into 3. So naturally, to describe a point, you see, what I do is I think how many sticks do I need to get to that point. So if the point lies in the first region, then if I write 1/3 plus, 1/3 plus, I'm already a little bit out. Maybe if 1/3 plus everything else is 0, then I get this 1 point. But aside from this 1 point, 1/3 plus will get me outside of this first interval, right? So that's why this is 0.0. I don't want to move by a whole fraction of 1/3. So maybe I want to move by a fraction of 1/9. That's fine. And maybe then 1/9 plus a little bit more, right? That's fine. So what you do is you move by the maximal amount, so that you don't escape the interval, by the maximal amount where the denominator is 3 to some power. Okay. So in this case, this would be any point in here will begin with 1/3 plus, because I have to first skip the first interval, and then I need to move a little bit more distance. But if I want to get to this interval, right, what do I need to do? I need to actually add 1/3, another 1/3, so 2/3, and then a little bit more. Okay, so that's why this is 0.2. Good?
So is 0.3 equal to 1?
0.3 equals to 1, exactly. We don't represent 0.3 because of it, right? In the decimal expansion, you always write the fraction smaller than 1. So that's why we don't allow 0.3 or values that are bigger than 3, because that means we're skipping by an integer. Okay? So that's why Bn is either 0 or 1 or 2. Because remember the way we did with the supremum, or basically the way we showed that, that such a representation is always possible. We can always find, let's say, an infinite representation of that form by calculating a supremum. So you just go as much as possible, but not beyond. You remember that argument. Okay? So you see why we choose this, this representation. And now the question is, can you figure out what is a representation for elements that survive in the Cantor set? Right? Because you can see that I don't write it here, but I said left, middle, right. The middle is always removed. So what survives is left or right.
It's the zeros and the 2s.
That's right. It's only the zeros and the 2s, and you see that there is a little bit of a nuisance, 1/3. 1/3 can be represented as 0.1. Okay? But aside from 1/3, any number that is smaller, that is strictly inside the interval, you need to write 0.0, because if you write 0.1, you already are out of the interval. Okay? So this is the observation we make. So notice that elements that if X is an element in the Cantor set, then X can be written as let's write it, 2A1, 2A2, 2A3, and so on. Where A1 is either 0 or 1, that's the same as saying that the coefficient at B here is either 0 or 2. So let's write it mod, or not mod, let's say base P, base 3, where AN is either 0 or 1. You see that? So, so we might look at the endpoints of the interval. So what endpoints like 1/3 can be written as 0.1, but then I can also write it as 0.02, and then go on. You see, basically, I know I can represent them in this form because I can follow left or right sequence. So how do I arrive at 1/3? I go left, and then I continue going right, forever right. How do I get to 2/3? I first move right, and then I go forever left. So all endpoints can be characterized by eventual motion to the right or eventual motion to the left. Great? So you see how you characterize the endpoint. So 1/3 is 0.1, but it does have a representation in either, the coordinates are either 2 or 0 in base 3. Okay, let's look at 2/3 for a moment. What about 2/3? Another endpoint. So what is 2/3? 2/3 is 0.2 and then followed by 0 bar. It does have another representation which is 0.1 followed by a lot of 2's. Right? That's in base 3. But notice that at least, so this is an endpoint, so one representation is wrong, but it does have another representation which is right, which is of the form zeros and twos. Right? Well, let's see, for example, what's the representation for 1 that we will pick. So, or actually, let's pick maybe, let's pick 1/9 for a moment. What is 1/9? It is in base 3 immediately without doing any thinking. It's 0 point what? 0 point in base 3. 0, 1. Agreed? This is not quite the right representation. What does it say? It tells us that, well, I don't need to move by infinite fractions. I can just not move by a third and then move by 1/9. One third squared, okay? You see what this means? This just means 0 over 3 plus 1 over 3 squared. That's why it's base 3. That's what it's called decimal, but decimal means 10. So what's the language? Tertiary representation or base 3 representation. Okay. But so this is 1/9 is not quite the right representation. Can you give me another representation that will make it good? That will make it the characteristic that I'm trying to tell you it has. What's the other? What's another way of writing 1/9? 0.00 followed by lots of 2's. Okay, in base 3. So you see, so you might say that the endpoints are the only ones that have the endpoints of some interval are the ones that have a different representation. That's not necessarily the Cantor characterization. So does it make sense? You see, I throw the statement out as if it's immediately obvious. Maybe it's not. You see how I know what's an endpoint? Just think about moving through the intervals, and you know that to get to an endpoint of an interval, you eventually just have to go all the way to the right. So you can jump left, right, but eventually, if it's a right point of an interval, you just move all the way to the right. And if it's a left point of some interval, you eventually move all the way to the left. So for example, how do I get to 2/9? I first go left, then I go right, and then I go left, right? So left, right, left. So what is left? Left means move by 0. Right means move by 2. Well, 0 over 3, 2 over 3. Or whatever the level, right? This first is level 1, so 0 over 3 to the first power, or 2 divided by 3 to the first power. In here, it's an extra motion by, now it's level 2, so it's 3 to the second power. Make sense? Let's see if you would understand it. So let's say I had a different procedure. There will be one homework like this, and it will be on the exam. Let's say that my procedure would have been to divide an interval into, let's say, 5 parts, right? So you would think, what is a good, and then remove some parts. I'm not sure which. I can say maybe every second part remove or something, right? So first leave, second remove, third leave, fourth remove, etc. If I divided it into 5 parts, what would have been the natural representation? In what base would you try to describe the things that survive?
Base 5.
Base 5, you see? Because that's really why base P works. We have this sophisticated proof using the supremum, but really what you do is you are trying to stack a bunch of sticks or segments of sticks which you cut by the same amount. So we usually try to cut by 10, but you can just choose any other system. Babylonians for some reason liked base 60. That's why we have 60 seconds in a minute and 60 minutes in an hour, because basically what they did is they cut 1 into 60 parts.
So what happened to 60 hours in a day?
Yeah, I mean, but then seconds for some reason, or for some reason I was surprised. I thought that you continue cutting it to 60, but when you edit videos, you have, milliseconds or something else. You actually start cutting it by a different rate, right? Right. So you actually transition into base 10. But minutes, seconds, hours, those are things at a rate of 60. Okay, that's what's derived from that time. So 60 seems like a very big number. Another natural base that you like is, I suppose, base 2 if you program, right? That's in some sense the simplest, right? Because you just cut into 2 parts. It's easiest to cut into 2 parts, much harder to cut into, let's say, 71 parts. Good? So, when you understand this characterization, I feel like, I don't know, something happened over the 3 years I have in total analysis. Somehow I feel extremely loose. Like what I'm telling you somehow is not inspiring enough. You look at me with fish-eyed faces. I'm not sure if you understand. All right, so let's try to ask a few questions if you get it. So, example. What you are going to try to tell me is if a particular number is in the Cantor set or not, based on the ideas we just described. Example, so is 1/4 an element of the Cantor set? What do you do, and how would I figure that one out? Yes?
You can try to write it as a combination of fractions with base 3 powers.
That's right, right? In base 3, I hope I feel like I haven't spent enough time on it, but I hope you understood why this works. So what do? I simply, we just go and remember how we did division in elementary school. So what you have is you write 4 and 1 here. So I want to know how can I express a quarter in base 3. So 1, you see 1 doesn't divide into 4. So what do? I try multiplying it by 3. 3 still not good. So I try to multiply it by 3 squared. Okay. So I write this instead of 1. I will write 9. Or 3 squared, and here I write 0. So notice 9, I multiply, so that means there's a 0 here, and if I take 9, what's the biggest number that is divisible by 4 that's lower than 9? This is 8, so, and 8 is 2 times 4, so this would be 2, okay, and then we have here minus 8, and what do we get here? 9 minus 8 is 1. And you see, once you get 1, you see that the process repeats. So the next thing is, so from here, you right away know that it's this bar. This thing is bar. So in other words, what is 1/4? 1/4 equals to 0.020202, etc. So and that's in base 3. So in other words, what I'm claiming is 1/4 is 0 divided by 3. Clearly, if I move 1/3, I move too far. 1/4 is smaller, right? So I move by 0 of a third plus 2 over 3 squared plus 0 over 3 cubed plus 2 over 3 to the power of 4 and onwards. Okay? So what does it mean? It means that in terms of the right and left, what does it mean? I move left, then right, then left, then right, then left, then right, then left, then right, and that I descend through a particular sequence of nested intervals, which gets me to a particular point, obviously, of the Cantor set. Yes? So this means it's an element of the Cantor set since I only move left and right. If I saw a 1 here, potentially, unless I can write it somewhere else, with some other way, it means that I am in the middle interval and eventually delete it. If there is a 1, then somewhere I jump to the middle. So what is 1? So 1/4 belongs to the set delta. Wonderful. We have calculated it. We know 1/4 is there. What about 2/5?
Professor, can you go over how you do that division?
Yes. What do you do when you do division in base 10? You multiply by either 10 or 10 squared or 10 cubed. No? That's what you do. Let's see if I can try to explain it another way, right? So if I look at 1/4, let's see why this procedure is just an algorithm of what I think what's happening here. So 1/4. I want to write it as powers of 3. So what do I do? So notice. So I might try to write it as 3 divided by 4 times 3. Correct? That's the same fraction. Why do I put a 3? Because I want it in base 3. I want to see denominator equal to 3. Yes. Now this is not good enough. 3 does. I cannot. You see, I don't want to cancel this 3. I want it on the bottom. Correct? So I want to remove. I want to remove this 4. I want to get rid of it. So what do? Then they say it's not good enough. I need to multiply it by 3 squared. Okay? Because I want a 3 on the bottom, or 3 squared on the bottom, or 3 cubed on the bottom. So I multiply it by 3 squared. So this is a 4. This is a 3 squared, and this is a 3 squared. Oh, now this 3 squared and this 4 I can reduce. Why? Because I have this, what do you call it, this remainder, right? What is 3 squared? The numerator can be written as 2 times 4 plus 1. You agree? Right? The numerator I can write as 2 times 4 plus 1. And the entire thing is divided by 4 times 3 squared. And I distribute. So what do I get here? I take this part in 2 over 4 divided by it. So what I get is 2 divided by 3 squared plus 1 divided by 4 times 3 squared when I distribute it, okay? And you see what happens here? Now you see that this is this is 0.2. That's how this is 0.2. It's like 0 over 3 plus 2 over 3 squared. And what is this? This I have another fraction, so I now try to deal with the other fraction. Does it make sense? Yeah, this other fraction, look at it. Why does it repeat? So look at this other fraction. It's like 1 over 9 multiplied by 1/4. And then I have this representation repeated. That's why repetition is going on. Do you see this? So this is 2 over 3 squared plus 1 over 3 squared times 1/4. And you see, and then 1/4, I then use recursion. You see, 1/4, oh, it's this plus that, right? And then again, recursion, this plus that, and I continue doing this, and that's how I get this this situation. So it's just a simpler way to put it in a table. So if you remember division from, I don't know, 1st or 2nd grade, you did the same thing in base 10. I didn't remember it. I completely did not remember any of it. But then when it came to the Cantor Set, I thought, what did I do at that time, right? And I did something like this. Make sense? Let's see if it does, because I'm going to give you a harder example. So this is just, I'm doing the same thing. That's what I'm doing conceptually. This is an algorithm. So another example, let's try to see if 1 over 5 is an element of the Cantor set. 1 over 5, is it an element of the Cantor set? Go ahead, do the calculation. All right. How are we doing? Let's try to see if we can figure this one out. So we use this division procedure. So let's actually, I prefer 2 over 5. Maybe 1 is boring, sorry.
No, it's too long.
Sorry. Do you want me to do 1 over 5 or I wanted, because we did 1/4, I actually preferred, maybe another number. Right. So, sorry. So what do I write here? I write here a 1. And here I write a 5, then maybe we'll quickly do 2 over 5 afterwards, okay? So this is 1 and 5. So clearly not good, so we write 0 point, right? And then you see what we do here, 1 is not good. What do we need to multiply 1 by to be able to divide by 5?
9.
3 squared or 9, right? So 9, so that means there is an extra 0 here. Now this 9 and 5, what do we have? This goes only once, so what we have is 4, right? So there is a 1 times 5, and then we subtract 5, and what remains is 4. Yes? What remains is 4. Now what do I do with the 4? How much do I need to multiply it by? 3, right? So I need to multiply it by 3. I'll write here 4 times 3, which is 12. And then we have here a 2. And 2 times 5 is 10. Subtract, so we have 2. Oh, wonderful. I don't even need to do 2/5 because already this is like 2/5. Okay? So whatever the expansion afterwards is like 2/5. Oh. So what follows afterwards? By the way, you can wonder if you need to continue, right? But let's finish it, I suppose. So there is a 2. So if there is a 2, what do I need to multiply this 2 by? I need to multiply this 2 by a what? This 2 is multiplied by 3. So we get here a 6. And 6 contributes 1, so there is minus 5. And then, we are back to 1. And if we're back to 1, what does it mean? The process starts all over again, right? So we're like 1/5, so the process goes all over again. So this is my representation. So what I have is that 1 over 5 equals to 0.01 to 1 in base 3. Is it an element of the Cantor set or not? Is it an element of the Cantor set? Yeah, of course it's an element of the Cantor set. Not because what is the one here saying to us? It means that in many places we move into the middle. Right? So look at it. First we move to the left. First survive, but then we move into the middle. 1. So first level it survives, but second level it had to be deleted in the Cantor set because in the second level we have a 1 here. Yes?
So it can only survive with a 1 in it if the 1 is the very last term.
Is the very last term, exactly. Wonderful, right? So there is a 1. Okay, does it mean it doesn't survive? No, not yet. But then we see afterwards it goes into 2. What does it mean? It means it's well inside of the middle interval. Do you see this? This 1 means that in the second layer it's in the middle interval, and then it's in the right of the middle interval. Do you understand that? This 2 afterwards means you're in the right of the middle interval, right? It's deleted. It's you see basically if there is a 1, it's like, oh, I'm about to be deleted, right? Woo! And then if you stay right, that's wonderful, right? So you understand. Remember this very simply, right? You have to if you're an endpoint, that the endpoints are the only problematic ones. It means either it can be expressed as 0, you're in the left. I'm making it too complicated. Endpoints are what? Are the ones that are eventually either entirely 0 or entirely 2. Those are endpoints of intervals in base 3. Do you agree? Because endpoints, you are just always moving right, or always moving left. So this is not.
factorial?
3 factorial. Means it doesn't, right? Very, very strictly it doesn't. All right. I might digress in a moment. I'll try to do it briefly. So before I actually digress, let me just mention yet another important property of the Cantor set. Let's try to think about how much of the Cantor set is there, right? How much of the Cantor set is there in terms of, you see, we remove middle thirds. How much of the material that makes out the Cantor set survives? If it were made out of a wire, a thin metal wire, how much of that wire will survive after we carry out the deletions, right? We cut the middle thirds and we cut on and on, right? So this is the question, more precisely asked in measure theory, but how long is the Cantor set? And what's the answer to that? Well, let's look at the first interval, right? So let's look how much was deleted, right? Let R be how much removed. The length of intervals removed. Length of intervals removed, and how much will that R be? So let's look at the first removal. I'm hoping you can see it. I don't want to draw a picture. So the first removal, how long is it?
1/3.
1/3. So the first removal is 1/3. In the second stage, we have 2 removals. You agree? Because there is left interval surviving and the right interval surviving, and we remove the 1/3 of each. So how much is removed in total on the second stage? 2, because 2 copies of the same length, 2 9. So 2 3 squares plus the next stage. You see, we have 4. So they're going to be 4, right? So it would be 2 squared. They double the amount of removals over 3 cubed, etc. Okay, so what is this equal to? Remember that you can of course do it rigorously, but remember that you can very simply look at it, and maybe this repeated sum, it has similarity. Whatever is in the red parentheses is in a way similar to the entire thing. It will be completely similar if I factor out what? So you look at R. R is equal to the sum. In the red parentheses, I want to see the same sum. What do I factor out to accomplish this? I'm basically teaching you elementary series, basically infinite series or power series for children. So that will be 1/3 plus. How much do I factor out? You see, this has to begin with 1/3. So I factor out 2/3. And then what's left in here is 1/3 plus 2 over 3 squared plus etc. Right? Because it's infinite. Do you understand the idea?
Okay, so what's the point?
Yes? Do you see what I just did? You see, basically I look at this infinite sum and I just look at the tail of the sum. You know, I just forgot about the first guy. I look at the tail of the sum and I can strain my imagination and see, well, it looks very much like the full sum. All I need to do is factor out 2/3 and that will be exactly the same sum, which means that I have this equation. I have R equal to 1/3 plus 2/3 R. Right? Because what's in parentheses is that same sum. Cool, right? You remember calculus 2? You did those sums in calculus 2. So I'm just showing you can do many of them easier. You can kind of quickly jump and get to the answer. So what must we get? So I take this, I move across, so that means that 1/3 r equal to 1/3, and so r is equal to 1. Isn't that interesting? Basically what was removed, how much length have we removed? We removed all of it. We removed the entire length. So let me briefly digress. It's still on the same topic. There are analogs of the Cantor set, many analogs in 2 dimensions, 3 dimensions, etc. Okay?
So the most famous is like a cube that doesn't have volume.
Right, exactly, right? So I actually, in parallel to this class, I teach thinking mathematically. It's a morning class tomorrow, and you know, they don't particularly like me. I do my best to like them. So I explain the stuff to them as well, right? So there is this, for example, 2-dimensional analog of the Cantor set in which you remove, you basically cut the unit square and you remove the middle ninth. You see that there are 9 equal squares. You remove the middle ninth, and then you cut the remaining ones and you remove the middle ninth. And if you do a similar calculation, you just do it a little carefully, you find that what you remove is pretty much everything. You remove a full area of 1, right? So then I mentioned that such a thing, right? Such a process is used, for instance, in constructing antennas. It definitely was used in cell phones, perhaps still used in cell phones. And if you look into Amazon, this is a version of a triangle. It's again another version of the 2-dimensional Cantor set. It has different properties, by the way, but another version of it. And this thing is used as an antenna. Okay. So I mentioned this in class, and actually I think my brother overheard it. And I mean, I just see that he has a lot of windows opened, and I see him looking at this picture. I thought, oh my God, my brother actually is interested in understanding this fractals, right? And then what I found out is, again, what he wanted is just to buy an antenna to attach to his Infinity IQ30, which he actually bought for $300. Remember that, right? Yeah, so he actually got this thing to attach. He couldn't care less about how much material is used. And to my thinking mathematically class, I tell them, well, you see this piece of metal. How much material do you need to actually manufacture it? Based on the calculation we did, or a similar, you manufacture it out of nothing whatsoever, right? You just kind of go abracadabra and it's there. It's the same thing that happens with the Cantor set, so it should kind of surprise you, right? We deleted everything and we were left with uncountably many points. So we delete everything and we have an antenna. How beautiful is it? Is it, right? And yet, maybe one more digression that I want to make. It's you see the Cantor set and analysis. Maybe that's why I'm not teaching it as well this semester as I used to, at least not from my memory. You know, analysis has been a blessing, and of course now it has become my personal hell. Right? It is. So I often had a dream like this. So not quite. You can see it, I guess, right? You see this this thing. So here I tell you, I don't really dream this particular picture. It's actually more ugly. So what I dream is that I'm in a space where the closest, basically a point that seems infinitesimally close to me is infinitely far. I can never move. I can never get anywhere in life. I can never go anywhere, right? And that's and I thought when I woke up, is this truly so? And indeed, right? A very simple, easy example is the Koch curve. You see that this is of length 1. Here, what you do is you delete the middle thirds, but instead of just keeping it empty, what you do is you stick an extra copy of 1/3, and now you have, and of course there is no room, so you put it in a triangle form. Do you understand? So what you did is you deleted the middle third, or maybe you lifted it up and made another copy. So now it's connected. what have you done? So the point from here to here used to have 3/3 of a length. What is it now? It is 4/3, right? So to travel to this point, you have to travel 4/3 of a length. Now what you do is, for each of those sides, again, you delete the middle thirds and replace it by 2 of them. So how long is this? So this is 4/3 times the previous. You understand? In the next level, the distance from here to here is 4/3 times the previous. So if you remember, by the Archimedean property, 4/3 to the power of n goes to 4/3 to the power of n, as n accumulates and grows to infinity, goes to infinity. And so you might wonder, okay, from this point to that point, it will take you forever. It will take you an infinite distance. But from any point here to here, it would also take you infinite amount, because it used to be just a small length, and now it was multiplied by 4/3 enough times to be infinite. Although, so it's basically every point between any of them, there is a crunched, broken, jagged line. And this is very pretty because it's regular. I can show you, I already did it. I told you I'm scared of pancakes, right? So the pancakes is the actual thing that I have to deal with all the time. Every Friday, sometimes every Tuesday, and every Thursday. All right, back to the Cantor set. All of those are analogs of the Cantor set, which in a few years you might be dealing with yourself if you are not lucky. So the next topic, if we have time for it, is again, we want to see yet another argument for why the Cantor set is uncountable, and not only uncountable, right away we can see that it's the same size as the full real line. In other words, it has the same cardinality, the same quantity of elements as the full number line, even though it occupies 0 space. Occupying 0 space makes it, by the way, nowhere dense, if you still remember it, right? The Cantor set, as I described it here, is nowhere dense. It's already a closed set, do you agree? What you do is you delete open intervals, so what remains is obviously a closed set, because the complement is open. So it's a closed set, and if you take the interior, could it possibly have any interior? Interior means having an interval, but an interval is of a particular fixed length, no matter how small. But that length had to be cut. So points that survive on the Cantor set, they're like people on a sheet of ice that continues to be broken between them. They're always apart. So now we talk about the Cantor function. So the Cantor function is going to do the following. So let x be a member of delta. Then x equals to 0.2 a1 to a2 to a3, etc. Base 3, where an is equal to 0 or to 1. Do you agree? So by multiplying 0 by 2, I get 0. By multiplying 1 by 2, I get 2. So that's one way to write an element of the Cantor set. And this representation is unique. This representation is unique. Do you see why it's unique? Unique because we mentioned before that left and right sequences have a unique, left and right sequences give you a unique address of each point of the Cantor set. Correct? So this is just describing how the address of zeros and ones, lefts and rights, can be translated to an actual geometric point, right? Because what you do is you translate the sequence of zeros and ones into how much you have to move away from zero to get to a point of a Cantor set. So this representation is unique because the intersection of nested intervals that go to zero have a unique point at which they intersect. So uniqueness follows from the nested interval theorem. So what the Cantor function is going to do, the Cantor function is going to take this x, look at its representation, and convert it to a base 2 representation. Oh, sorry, so there's no f here. So it's just 0.A1, A2, A3, but base 2. So in essence, what is the function doing? It converts one power series that has 3 in the denominator to a power series that has 2's in the denominator. So what we have is f of x equals to f of the infinite sum which will be the summation of a n over 2 to the n. Good? So it only works if you're able to pick a point in the delta, because what will it do if the number is not divisible by 2? So 0 divisible by 2, and 2 is divisible by 2. But if I have middle thirds interval, there is a 1, I cannot really convert it based on this procedure to base 2 series. Okay? So several things are obvious about this function. So notice that f from the Cantor set to the interval 0, 1, because you see it always converts a fraction to a fraction, is onto. Do you see that it's onto? It's obvious because take a sequence of zeros and ones and just multiply those zeros and ones by 2, and you have the input that will create it. You understand what I'm saying? Look at the sequence. So for example, here, example. So suppose that you have y belonging to 0, 1. Y can be expressed uniquely as an infinite series in. So I can write y equals to 0.A1, A2, A3, etc. Right? Where A1 is either 0 or 1. There is only one representation that is available to you. Well, actually, sorry, not one, but regardless of this representation, A's are all either ones or zeros. Okay? So there could be two representations. Maybe one ending in 0 and followed by ones, or one that is ending in zeros. So some numbers have two representations, but most numbers have only one. So if this is your y, then what should be x that's mapped here? So what x is mapped? So any y in between 0 and 1 has a representation in any base p. In particular, has a representation in base 2. So we can write y as a bunch of sums of halves. So what x is mapped by f to y? What x is carried by f to y? Obvious. I just picked some representation. So maybe So what is x equal to? X will be equal to 0.2a1 to a2, etc. in base 3. So that x will be, by the way, because it's written as 2a1 to a2, etc., it's already automatically in the Cantor set, and the function will transition it to the point that you want in the codomain. So what I'm saying is, that if I take y to equal, for example, 0.1, 0, 1, 1, etc., then that's the same as saying that y is equal to 1/2 plus 0 over 1/2 squared plus 1 over 1/2 cubed plus 1 over 1/2 to the 4th, etc. And what x is carried, so I can take x equal to 2 over 3 plus 0 over 3 squared plus 2 over 3 cubed plus 2 over 3 to the 4th power and onwards. And this x is carried by f to y. Do you understand? It converts base 3 to base 2. So automatically, what does it imply? Automatically, you know that that the cardinality of delta is bigger than or equal to the cardinality of the interval 0, 1. You see why in the language of cardinality, think about it, right? So how do I know that I'm holding that I'm holding more elements on my right hand than elements on my left hand? One way to know that is if from my right hand I have an onto function. You see, it doesn't have to be 1 to 1. Here's an onto function. That means that from here to here, this cardinality on the right hand is not less, bigger or equal. Okay? But since this is part of R, we know that they are equal. So that's equal to the cardinality of R. But since delta is a subset of R, the cardinality of delta, in fact, has to equal to the cardinality of R. Agreed? So that's just another argument. I'm not sure if it makes it easier for you or not, but another argument to see that the cardinality of delta has to be the same as the cardinality of the entire real number line. So another thing that you should notice about this function, and this is perhaps less obvious, maybe I'll leave it for you as homework. So notice that if x is less than y, then f of x, and what's the relationship between f of x and f of y? So in this case, I mean, x and y are in the Cantor set. So forget about the y I wrote above. It's a different y. This is just I'm claiming that suppose I pick x and y and they belong in the Cantor set, and I find that x is a smaller point in the Cantor set than y. Then what's the relationship between f of x and f of y? What do you think? Look at what the function is doing. So if y is a bigger number than x, what does it mean about the tertiary expansion of y and the tertiary expansion of x? I will see that in y, the fractions that I add are going to be bigger. Definitely bigger at one point. I guess we don't see it. But we don't have time today. Maybe we'll talk about it, maybe not. You should try to see it. So this is f of x less than or equal to f of y, with equality happening if and only if the x and y are consecutive endpoints. It's important. We're going to return to this point when we talk about continuous functions. With equality if and only if x and y are consecutive points or endpoints, I should say. What I'm really saying is that, for example, x might be equal to something like x might be equal to 0 point, let's say 0, 2, 2, 0, and then 2, 2, 2, bar. Okay? So you see what I'm saying, right? So this is what sort of point? Can you describe it? X is what sort of endpoint? Left endpoint or right endpoint? So look at x, right? So what does it mean? First I move to the left, 0, then I move to the right, then again to the right, then to the left, and then right, 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 right. What sort of point is x? It is a right endpoint, right? Because you see, you're just jumping around, and with some interval on a certain level, you're just going to be the right edge of that interval. Okay? So if x is equal to this, and then x smaller than y, and f of x equals to f of y, then y must be which point? Then y is the point 0.2, 2, and notice this is where you have the repetition. So there is a 0 here. Here, look at here. There is a 0 here. So what must be here? What must be here? It must be the right interval. So there must be a 2 here, followed by zeros. Okay? If f of x is equal to f of y, that's the only possibility. Only the endpoints of the consecutive deleted intervals. So in other words, at some point, x and y, they used to be in the same interval. At some point, they are in 2 different intervals. At some point, x is in the left interval, and y is in the right interval. Okay? Because the way they separate, y is here to the right, and x is to the left, so they separate by a middle third being deleted. So they're isolated from one another. The only way that happens is if x is, so if they survive, so x has to stay for this equality to hold as close as possible to y, and y has to stay as close as possible to x. So it's kind of like you have this person that you love. Maybe you're a polar bear, and you have your polar bear companion, and you say no, right? And we are on the, and basically they try to stand as close as possible to one another, right? As they are drifting apart on their icebergs, like this, right? They're trying to stay as close as possible. Then the function will map them to the same point. At least, right? At least when when you convert a basis, they are together somewhere above. Goodbye.